Good morning. I'm Cédric Demeure, VP in Research and Technology in Thales, and such Director of the Research Center in Palaiseau, south of Paris. My talk this morning will specialize in presenting you some trends in CPS, CyberPhysical Systems, and the underlying technologies. As such, I'm also the president of Embedded France, an association dedicated to embedded system in France, and dedicated to animate the ecosystem of embedded technologies, both software and system. And the idea is for this association is to bring all the actors together to help them master those technologies, identify the trends, and so on. And you can find on the slides the link to our website, where there's lots of information concerning our members and so on. The association is organizing every year the Assises de l'Embarqué, which is a one-day workshop on embedded topics. We also distribute some trophies on embedded systems. And Embedded France is also has a role in a CPS for EU project, which is an Excel European project started a year ago. And this talk, in a sense, is also part of the dissemination activities in this project. As the president of this association, I'm also a member of the office of the Filière Électronique, the electronic competence industrial filière in France, and as such we discuss with all the hardware, the ESMs and all the other actors in the electronic world. Of course, I will not go through cyber-physical system definition, but as Edward Lee was definition is the integration of computation of sensors and physical processes. In other words, a cyber-physical system is a system that is able to analyze, measure what's going on in the world, in the physical world, and act upon it through actuators. And of course, as you can imagine, CPS systems becomes much more complicated as technology advances, and lots of new technologies are allowing more complex interactions, artificial intelligence embedded in those sensors, and so on. Typical cyber-physical system examples, of course, encompass smart mobilities with autonomous cars and all the traffic management that goes around it. In aeronautics, of course, there's more and more embedded complex systems with additional constraints like safety, criticality, security, of course, and weight, consumption, and so on. Energy systems are more and more using in cyber-physical systems, and of course transportation like rail and metro are also more and more using these kind of products. And it has to be seen as a global value chain, from the components to the boards to the products, the sensors, the overall product, like for example an autonomous car in smart mobility, but also it has to take into account all the communication means, and of course the cloud that drives the system of system, like for example traffic management in the case of smart mobility in a town or so. But you have not to forget everything that makes this possible, which means taking into account the tools, the software, the tests, and the productions equipment. So this makes an overall value chain that is rather large, and this is from an Artemis slide. You can see that you go all the way from the components to solutions, and you apply those solutions in the various systems, like of course transport or health or energy, etc. So you have to realize that it is becoming more and more important to take into account the whole value chain when you design every single element of that chain. And for another example coming from Thales, of course it's easier for me to present such examples, is what we call mastering the critical decision chain, especially in the defense market, where the sensors have to be very well mastered and used, and the data transmission, the data processing, and more importantly the decision-making process have to be defined and used in a very coherent way, with a lot of protection from end to end, security of course, but also communication means, most of the time radio in this particular case, and everything has to be coherent and optimized in a similar fashion. So more and more we are coming from a world where safety critical was really the product on the field, like a train, like an airplane or a vehicle or whatever, and then you had data criticality in the cloud domain and with the security issues, and more we are adding communication means, which means that those two worlds have to be optimized together, and more constraints come from one world to the other, from what we call operational technology to information technology and vice versa. And so you end up having a global critical decision chain from the field to the cloud or vice versa, where both worlds need to work in a coherent way with the other, and you have a continuum mixing of the constraints. The security goes down now all the way to the product at the embedded part, as well as some of the way to work and distribute the processing needs to be done in a continuous way throughout, in this particular example, for example, from the embedded product to the gateway, to the edge, and of course to the cloud. And this is a very important trend in most of our electronic markets, where you can apply this to the autonomous car, you can apply this to defense, you can apply this to communication, and so on. And this comes, of course, in a world where computing is also evolving very fast. Of course, the end of the Moore's law implies that you have to work differently, and hardware optimization is a way to do this, but it becomes more and more difficult to have a single solution that fits all the problems. You need more and more to have heterogeneous solution to be very optimized for the various parts of the computing that you need to do. And you need to be able to include very complex systems with system on chip and various software, various firmwares, and so on, with added safety and security constraints, which means that hardware usage, especially COTS hardware usage, is becoming very more difficult, very expensive, and more importantly, in a lot of cases, suboptimal, where there's lots of things in a standard processor that you don't need in particular cases. And so it becomes more important to be able to design your processes, or at least your computing solution, in a way that it exactly fits your need and just your need. A trend that starts to be very interesting to be able to propose a solution to this is open hardware. Open source hardware is becoming more and more a very interesting solution to this kind of constraints and of problems. Not only from a technology point of view, but also from a mastering the technology point of view. And of course, everybody knows the actual Trump's US president ban on the use of certain technologies for China companies. Well, this may not be the only places where this kind of ban may occur, and we have to be able to be ready, to be independent, to be sovereign, and being able to master our technology and our provider in such a way that these kind of bans don't affect us. And this especially is important, and RISC-V is a solution that is rising in the world to be able to cope with these problems. RISC-V is just, in a sense, an instruction set architecture with a list of a lot of details, but it may be seen as just an interface, but interfaces are really at the core, at the center of the solution, as in the sense that they influence the performance, the complexity, the security, and so on of your solution. And one of the most important interface that people have a tendency to forget is the interface between hardware and software, which is especially important in embedded systems. And these have to be kept simple and smart in such a way that your design is as simple as possible and fits exactly your need in a reusable fashion and so on. And this is exactly what the open source hardware community has been doing by introducing RISC-V. And the ecosystem is becoming more and more important, with lots and lots of actors embracing this technology, from the software, embedded software part, to the tools, to the hardware itself. And you now have a real important ecosystem in which you can find all the parts that you need to build your own solution. And this is becoming a very, very interesting and important solution, which, in my belief, is a very important trend in embedded system these days. And you can find already lots of multiple hardware implementation of RISC-V processors. For example, from India, with the Schottky processors, seven classes of processor, from high power processors to very limited embedded low footprint solution. Other solutions like the Ariane processor from KTH in Switzerland is another example. Microsemi is coming up with processors and so on. So you can see that more and more providers are embracing that technology, and it is becoming easier and easier to get your hands on those. Open source hardware is, of course, designed in such a way that you put in open source not only, of course, the interface, but the schematics, the topographies, the build of material, the drill, the pick and place. You can go all the way to the HDL sources, even the mechanical sourcing and the drawing, and of course the firmware that goes into your processor. So you really have a complete set of solution that is available for people to use and design your own solution or your own product. For example, in the case of Thales, in 2019, in collaboration with the Indian Institute of Technology, we designed what we consider the first multi-core RISC-V processor for safe and secure critical applications. This was based on the Schottky Class C processor. It's a multi-core architecture, and the idea was to design this processor for spatial and critical solutions with a spatial and temporal segregation of the applications and the process. And it was designed for mixed criticality application. And our affiliate Cisco has designed a specific version of their PikeOS operating systems to run on this processor, so that we have a complete set of solution for the various business lines of Thales to be able to use them. So another trend that I would like to stress is what we imagine to be one of the next step of open source applied to this kind of solution, is to put software-defined everything everywhere, in the sense that if you have a small enough footprint processor, you can embed this processor within ASICs for analog design to be able to configure on the fly the processor, to be able to have different application, to have different interfaces, to have different routing, for example. And even if you take into account safety critical and all the necessary certification issues that goes with it. And in that sense, we really believe that this kind of technology will be able to provide a solution to the various markets that are important for us. And in a sense, open source leads to open innovation because it removes upfront barriers through open standards and the fact that you can have access to examples, you have access to a real modular solution. You have innovation through the design, through the from the IP to the language. The same goes through the validation process. The gap between software and hardware is completely bridged in the sense that collaboration is made much more easier because the languages underlying those open source may be the same or similar. And it's also a new way to collaborate in the sense that you can have access to GitLab, for example, to GitHub, to hackathons type of work. And you can take all those very nice way to work and design coming from the software world down to the hardware one. It's just exactly the same way. And an example is, for example, is the fact that an FPGA becomes now a service. Silicon might become just a service. You just pick and place all the things you need, hardware-wise, software-wise, and you can have all the necessary workbench and everything works together. And it provides a perfect solution to embedded systems. What is also important is that open source is a way to be resistant with, provider issues, because if your provider is being bought by a competitor, it does not mean that you have to restart everything from scratch because you have open source, so there's no IP issues, there's no property issues, and this might make a very resilient solution to designing a product and mastering your complete value chain from the component to your system. And the fact that the community is becoming very important ensures that there is a stability in the design chain that is really resilient to all the things that can happen in the commercial world. I'd like to finish with an example of a collaborative advanced project in this area of CPS systems, and which might be another very interesting trend, is the idea of defining pre-integrated modular architecture. And this project is CPS for EU. You can find the website is here on the slide. It's an Excel. It's a project under the Excel joint undertaking that started last year. It going to last 3 years. It's a rather large project with a budget of 53 million euros. The man-month effort is around 5,000, so with 36 partners, so it's a rather large project. Some SMEs, some large groups, some technology providers, and so on, with lots of various use cases and pre-integration architectures. So a very wide project that is tackling this approach of having pre-embedded, pre-integrated architectures. Here's a view of the consortium with 11 large companies, of which Thales obviously is one of them. Valeo is the leader, and you have some large companies in Italy, in Germany, in France. Same 14 SMEs, which are mainly technology providers, and 11 academic and RTOs providing also technologies. And as you can see, 2 dissemination organization, and Embedded France being one of them, the other being Captronic. Captronic is an association in France helping SMEs embark in the new digital world by providing help, training, and these kind of services. As I was mentioning, CPS for EU is really tackling pre-integrated architectures. So you have basic modules of various types that are pre-integrated to provide computing solution, connectivity solution, sensing solution, and cooperative solutions, so distributed work and so on. And then, of course, this is going to be used in various use cases in the automotive world, in the industry automation world, and in at least one other industrial sector, which is energy. And these complete projects provide tools, provide building blocks, and but what is very important is this notion of pre-integrated architecture, where it's not only modular architecture, but it's a pre-integrated, so you don't have to reintegrate some of the blocks if they have been already integrated before, and you can use them in various solutions as is. To finish, I would like to stress the fact that what is very important now is to take the overall picture into account, not only the product, not only the system, but the global solution. And the interaction between the solution in terms of constraints to the embedded product, for example, has to be taken into account. And we have now in Europe a very good position in industry. We are not as good for consumer products, but for industry products, there's really, we need to be able to continue to master those technologies, to be able to keep our leading position in that domain. So the major trend I was mentioning, and I believe is very important to our industry, is open source hardware, and the fact that designs are becoming very important, that takes into account open source hardware with open source software, and I really would like to stress the importance of this approach for sovereignty in Europe and for the industrial independence and resilience in this more and more competitive world. And the trend also that I mentioned at the end is the fact that modular design is a very good idea, but we can go further, and pre-integrated building blocks is really a new approach that this CPS for EU project would like to stress and provide solution to the market in this domain. And this, we hope, will bring intelligent high-level reuse with pre-integrated architecture. And this is all. I would like to thank you for your attention, and I'm, of course, open for questions. Thank you very much.